This video, we're going to do some practice problems with the counting techniques that we've learned. So we know the multiplication rule, the addition rule or inclusion-exclusion rule, the subtraction rule, and we know about permutations and combinations. So I'd like you to think about, everything we've got in order to take a look at these problems. So grab some paper, pause the video, spend a good amount of time trying out each of these problems, and then we will talk about these problems one by one. So try those out and we will talk about them together. Okay, so first 3 cards are selected from a standard 52 card deck. How many 3 card hands are possible? So 3 card hands, we could ask ourselves, does the order matter here? And are repeats allowed? No, we've got these 3 cards in our hand. We can't repeat the same card, so no repeats, and no, the order doesn't matter. It's a 3 card hand. There's no order to it. So this is 52 choose 3, or could also be written 52 choose 3. The formula for that is 52 factorial divided by 52 minus 3 factorial. Number of ways to select 3 cards from 52 in an ordered way, and then dividing also by 3 factorial, the number of ways to rearrange those 3 cards. If we simplify that, we'll get 22,100. How many 3 card hands are there that are all jacks or all spades? So, or think addition. So this could be all jacks or all spades. So we'll put an or between them, plus. All jacks, there are 4 cards in the deck that are jacks, so 4 choose 3, plus how many cards are spades? 13 cards of each suit, so 13 cards that are spades, choose 3. And then we should subtract off the place where they are all jacks and all spades. So any 3 card hands that are possible that are all jacks or all spades, because by inclusion-exclusion we want to subtract off the elements that were counted twice. But here there are no such elements, right? Because there are no 3 card hands that are all jacks or all spades. There is 1 jack of spades, and so there's nothing to subtract. And so we've just got 4 choose 3, which is 4, plus 13 choose 3, which is 286. And so altogether there are 290 such 3 card hands. What if we're lining up these 3 cards in a row? So lineups, we're talking now we have an order to the cards. So what's the first card? What's the second card? What's the third card? Now we're still going to use the multiplication principle here. There are 52 choices for the first card and 51 choices for the second, and now 50 for the third because we're not replacing and shuffling. This is also the same thing as 52 permute 3, so we could also use the formula if we wish, and we would have 52 factorial over 52 minus 3 factorial, but that would give us the same thing. And either way, when we simplify our answer, we have 132,000 such 3 card lineups or such sequences of 3 cards. What about lineups where the cards are either all jacks or all spades? So again, we can have all jacks or, so plus all spades. And so all jacks, there are 4 jacks, so the number of 3 card lineups that are all jacks, 4 possible for the first card, 3 for the second, and 2 possibles left over for the third card. Or so plus 13 choices for the first spade, and 12 choices for the next spade, and 11 choices for the last spade. If we want to subtract their intersection, subtract the lineups where all 3 cards are both jacks and spades. Again, there are no such lineups because there's 1 choice for the first card, 0 choices for the next card because we took it away already, and 0 choices for the last card. So 0 times anything, we've got 0. If we simplify that, Then we'll have 24 for 4 times 3 times 2 plus 17, 16 for the next quantity, and altogether we've got 1,740 possible ways that that can occur. We could also write that as 4 permute 3 plus 13 permute 3. Okay, so now we're changing this one more time. We're saying now we are going to shuffle. So each time we draw a card, we're going to replace the card in the deck and shuffle again before drawing the next card. So how does that change our situation? That means that repeats are now allowed. Yes, we could repeat the same card twice. And does the order matter? How many sequences of 3 cards? So yes, ordered sequences are automatically ordered. So yes, the order matters here. So in how many ways can these be all jacks or all spades? So again, all jacks or all spades. The first card, there are 4 possibilities for that first card being a jack. And then we replace and shuffle, so we could technically draw that same card again. So this is 4 to the third is the number of ways that they could all be jacks, or plus there are 13 ways for the first card to be a spade, 13 ways for the second, and 13 ways for the third, again because there's replacement. Now we want to subtract off both with the inclusion-exclusion principle because we want to avoid double counting. And now we actually do have a possibility that the first card is the jack of spades, there's only one of them, and the second card is a jack of spades, and the last card is the jack of spades, that we just happen to pick the same card 3 times. So then that's 4 to the third plus 13 to the third minus 1 to the third, which is just 1. And if we simplify that, we will get 2,260. Next, we've got a party with 6 Americans and 8 Canadians, and they're going to select 3 people from the party to go and buy some pizza. In how many ways can this group be selected so they're not all from one country? So we can use the subtraction principle for this, that we want to just remove all possibilities that we're not interested in. So the number of ways where they are not all one country would be equal to the total of number of ways to select these 3 people. So we've got 6 Americans and 8 Canadians. There are 14 people altogether. How many ways can we select this group of 3 people? This is going to be unordered. It's just a group of people. There are no repeats. So this is 14 choose 3. And then we're subtracting the ones we don't want to include. So we don't want them to all be Americans, and we don't want them to all be Canadians. So if that's the case, then there are 6 choose 3 groupings that are all Americans. There are 8 choose 3 groupings that are all Canadians. And so in total, we've got 14 choose 3. If you calculate that out, that's 364, minus 6 choose 3, that's 20, and then minus 8 choose 3, that's 56. And so in the end, that's 288 groups of 3 that we could select, where everyone in the group is not from the same country. Next, we've got 20 people in a soccer league, and so they're going to pick a team captain, a goalie, and 10 additional players who don't have specified positions. In how many ways can this be done? So we've got our captain, and we're going to choose select a goalie, and we're going to select 10 more players that have no position, so unordered. So we've got 20 people to choose from for the captain, and then we're going to also have 19 people left over to pick for the goalie. And now of the 18 people left, we are selecting 10 of them to also be on the team. Because this is unordered, no repeats, we don't want to, if we select the same person twice, then we have one fewer person. So this is 18 choose 10 for that piece of choosing the 10 additional players. If you calculate this out, and let's just write it also as 20 times 19 times the formula for 18 choose 10 is 18 factorial over 18 minus 10 factorial times 10 factorial. If you calculate that out, you will get 16,628,040 possible ways for that to happen. So you might have also counted this in a different way. You might have also said, well, I'm going to select from all 20 people, I'm going to select 12 of them, 20 choose 12, and then I'm going to select one of those 12 people to be the captain, and I'm going to select one of the 11 people remaining to be the goalie. This would also get you the exact same answer, so you can do it in either way. Next, we've got how many lists of length 4 are possible from the letters A, B, C, D, E, F, G with no additional restrictions. So a list, you could also say that's a sequence of elements. A list is ordered, and it doesn't say that repeats are not allowed, so we should just assume that they are allowed if there's no other restriction given. So list can have repeated elements, order matters. So we have a list of length 4, 1, 2, 3, 4. There are 7 choices. There's 7 letters possible for the first. There's 7 choices for the second. There's 7 choices for the third, and 7 choices for the fourth. So that's 7 to the fourth, and 7 to the fourth is 2,401 possible ones. What if we have the restriction that the first letter is not an A or the last letter is not an A? So or should automatically make you think of the addition principle. So we want to figure out how many are there where the first is not an A or last not A. So the number where the first is not an A, so this is a list, and if the first letter is not an A, we have 6 choices for this first letter and 7 choices for each of the remaining letters. Or, so plus, the last letter is not an A, then we have 7 choices for the first letter and 7 for the second and 7 for the third and 6 for the last. But now we've double counted a whole lot of them. So we have double counted all the situations where first is A and last, first is not A and last is not A. So we've double counted a lot of these possible lists where the first is not an A. There's 6 where the first is not an A, no restrictions on the middle 2 letters, and last is not an A. There's 6 letters possible then for the last letter. And again, we're subtracting that off to avoid double counting. So all of those were double counted, both as having the first letter not be A and the last letter not be A. Okay, so now we've counted everything exactly once. So this is 6 times 7 to the third plus 6 times 7 to the third minus 6 squared times 7 squared. And when we calculate that out, we'll get 2,352. And lastly, how many subsets of size 4 are possible from the letters A, B, C, D, E, F, G? These are subsets. That means that order does not matter and repeats are not allowed as well. And so this is 7 choose 4, or also written 7 choose 4. So that's 7 factorial divided by 7 minus 4 factorial times 4 factorial. So let's just calculate that out for practice. 7 factorial over 3 factorial times 4 factorial. That's 7 times 6 times 5 times 4 times 3 times 2 times 1. That's 4 factorial over 3 factorial. That's 3 times 2 times 1 times 4 factorial. That cancels out with what we have above. So we have 7 times 6. 6 is the same thing as 3 times 2 times 1. That's 3 factorial. And so we're left with 7 times 5. That's 35 subsets of size 4 that are possible from those 7 letters.